Okay, so this is, if you're going on to college physics, typically the third chunk of physics is a lot of Coulomb's law problems. The Coulomb is a unit that you'll see a lot if you're doing any kind of electrical engineering, if you're doing any kind of electromagnetic physics. And it is, electrical force is force. It's measured in newtons. It's a force just like any other. It's an attractive force or a repulsive. The big difference is in things like gravitational force and forces where we're pushing on things and forces of tension, we're used to force having a magnitude really based on the direction in which the force is being applied. If I push something west, it has a westward force. If something is being attracted to the center of the earth, there's a downward force on it. Electrical force is a little different in that it can be attractive or repulsive. And it does get complicated fairly quickly. What I've typically chosen to do is we'll do some simple Coulomb's law problems. I'll show you what the dreadful Coulomb's law problems look like, but we're not going to do them. That way you've gotten your toe wet. If you're going on in physics, it's not like you've never seen a Coulomb's law problem, and you know what the dreadful ones look like, but we're not going there. So we don't do gravitational attractive force. You've seen it, you've felt it, you've calculated the force of gravitational attraction just based on mass gravity, but what you haven't done is problems for objects out in space. Because here's the cool thing, and I'm going to actually change the background for this. It needs to be the deepest, darkest color imaginable, and I'm going to put little tiny points of light all over. Just like, whoops, I didn't mean it to be that big. There we go. Little tiny specks. It's hard to see what's a speck and what's a dirt on my screen, but you see all those little things. So space is dusty. Hasn't been vacuumed in a very long time. That's why the sweatshirt that a whole bunch of boys were wearing at the beginning of the year that's got the guy sweeping space is one of my favorites. Space is full of gases and dust, and those are particles. Those are molecules. And it has been for a really long time. And we think that there is no growth. How many of you would agree with this statement? There's no gravity in space. You people know it's a trick question. You're well trained. If you go out in space, if I put you in a spacesuit and I kick you out the hatch, is there gravity act? I won't do that, I promise. Not that I think we'd ever find ourselves in those circumstances. Is there gravity acting on you? From where, Shane? You're nodding emphatically. Ooh, celestial bodies. Okay. So, having just watched the amazing documentary on Apollo 11, they fire the jets. They head out. Here, we'll draw a little Earth down here. Our beautiful little green and blue planet. I'm ever so fond of it. There's our beautiful little planet. Some squiggles of green. Continents, stuff, oceans, stuff. And they fire the jets. The moon is way too big. There we go. They fire the jets, and a beautiful little ship with humans on it starts to head out. They go this way. And once they escape Earth's gravitational field, they hit a point somewhere in the middle. And they do a really good job of illustrating it in the film, where they talk about leaving, how do they put it, like leaving the sphere of influence or something. And it's basically the point at which, based on some factors, which we're going to talk about in a second, the Earth is no longer pulling them back. There's no more influence from the Earth. So they cross that line, wherever it is, and I don't remember, but they really, you need to see the movie. I'm not drawing this correctly. Let's not be under any illusions that I'm drawing this correctly or to scale. So they hit another point where they cross into the sphere of influence of the moon. Where, and it's a point where they shift, and it's based on some factors which we're going to talk about in a second, which is going to explain why Vince is objecting to where I'm drawing this. What is gravitational attractive force based on? Let's see if I can do this cold off the top of my head. This one, which I'm sure I've got wrong, so if anybody's watching this and they think that I'm a stupid physics teacher, it's okay, I just didn't look it up. So This is Newton's law of gravitational attraction. And gravitational attraction is proportional to the mass of the two objects being attracted and inversely proportional to the distance between them. That's that, or the square of the distance between them. That's that radius. I think there's a constant, but I don't remember. Well, when we're on Earth and you have a mass, oh, you impressive thing, of 70 kilograms. What's the mass of the Earth? Somebody lightning finger that. Go. There, okay. So Earth has got a mass of, you know, let's just say 6 times 10 to the 24th kilograms, round numbers. Your mass doesn't matter, you know. Well, I thought there was an equal and reactive force between any two objects. I bounce on the Earth. The Earth exerts a force up on me. I exert a force downward on the Earth. Yeah, that's true. You are so tiny, it doesn't matter. Any two objects floating out in space have got an attractive force. We're going to get rid of these little guys. Oh, interesting. I left an infinity sign where the Earth is. So, you know, these two specks of dust out in space, it does look like a pig nose, doesn't it? Have an attractive force between them based on Newton's law of attraction. If we throw this tape dispenser and this pair of scissors out into space, they're going to be attracted to one another. But they don't do it on Earth because they're both so overwhelmingly attracted to the Earth. It's kind of like whispering in somebody's ear when you're standing next to a jet engine. The roar of the jet engine overpowers any kind of little subtle noise. So out in space, the little subtle gravitational attraction between two tiny objects is observable. On Earth, the roar of the jet engine, which is the attraction to Earth's surface, overwhelms all of that. Are we getting back to electricity and magnetism? We are, I promise. Coulomb's law looks an awful lot like Newton's law of gravitational attraction. So when we have two objects with a charge, the force of either attraction or repulsion between them is, now this one does have a constant, and that's why I can't remember if gravity does or not. Somebody could lightning fingers that if they want. Yeah, G, duh. When will I learn to get that one tattooed on me? So you're thinking about a sleeve? That'd be awesome. So the force between the two charged objects, and we very often at this level of physics think about what we call point charges. So we're thinking about like a single molecule with a charge. The force that attracts or repels those two things equals this constant times, and the way that it has to be written in slides makes it, I think, harder to understand. The electrical force equals K times Q1, Q2 over R squared, which looks an awful lot like the gravity equation. The magnitude of the charge of object 1, the magnitude of the charge of object 2, divided by the square of the distance between them, R squared, times Coulomb's constant. I always think of constants as a fudge factor. Gee, as long as I multiply everything by this, it works every time. Okay, well, let's multiply everything by this. We'll call it a constant. Good, that works. If we do dimensional analysis, we can prove that this is in newtons. So Coulomb's constant is newtons meter squared over Coulomb squared. And I should mention at this time, it's Coulomb's law. You can go research Coulomb. Good physics guy. Charge is measured in coulombs. So the words that you've heard associated with electricity are things like voltage and amperage. You probably haven't heard coulombs, but this is the level this is where we're actually measuring individual pieces of charge, and we'll do a little bit of that. So if we do the dimensional analysis, then we'll actually do sample problem 17A together tomorrow. What do we get? Gone. Ta-da! Electrical forces in newtons, just like anything else. So tomorrow we'll do 17A sample problem together. We'll work through probably 1 or 2 homework problems. We'll do the 2 easy homework problems, and I'll show you what the dreadful one looks like. And then we'll play with the styrofoam balls. Styrofoam balls are really easy because if you can charge those up, they have almost no mass. So the effects that you see on them are really easy to observe in terms of the forces of electrical attraction. So I think that's it for today.